course, having the answers make it easier. Okay, so I'm ready if you are.
It's already recording.
Okay, great. So this is a problem we did partly last time, or maybe a good part of it last time, but I want to redo that because it's a good problem. I did one big problem in the other class, which is too complex. We couldn't finish it, so I thought this is basically has all the elements we want, including two force members and so on, and it's feasible to finish it. So let's again start with step one, right? X, Y coordinates. Step two, okay? You just take all members apart. So I would say take apart, okay? Step three, draw all free body diagrams, and I had a special step, or maybe pseudo step, which was step 4, or part of the step 3, is note or watch out for two force members, okay? So all of these steps are part one of the problem, which leads to free body diagrams that you need. And I consider that 85% of the solution, because setting up the free body diagram is the key. So let's do that. So step 2, I'm going to take all these apart again. So we have this member, okay, a force P is coming here. Let's say these are the two unknowns, Bx and By at that point, and Dex and Ey here. So that's the free body diagram of this member, which I call the free body diagram 1. Okay? Then I have this member. There's only one unknown here at A because there's a roller there. At B, I would have to choose two forces in the opposite direction to these because of the law of action and reaction. If you two members are connected at a point, whatever forces you assume are acting on one of them, you should assume the same forces in opposite direction on the other one. Okay? At F, which is this point, let's say I assume this being Fy, okay, this being Fx, and at point C, we said what? We had one unknown because that is a special step. CD is a two-force member, two ends, only the two ends are connected to the rest of the structure. The two ends are pin connected, no load acts along that member. So that is a two-force member, or in other words, if you draw the free body diagram of that piece, this is 4 feet, this is 6 feet, okay? The unknown forces acting on this member would be acting along this line, connecting the two ends. So let's say we assume they are like this. I call this RD, this is RC. RC and RD would be equal, okay? And if I'm assuming that that member is subjected to a force like that, then the force here would be in this direction. So that's the free body diagram of member 2 and member 3. Obviously, of course, we always like to resolve inclined forces to their components, and we see that the slope here is 2, 3, square root 13, so this would be 3 over square root 13 RC. This would be 2 over square root 13 RC. Okay, one more free body diagram left, and that is for this member, the pulley. We have assumed these forces in those directions on this one, so this has to be on the pulley like this and like this. Now this applied load of 80 pounds, obviously this would be also 80 pounds. So this is free body diagram 4. Yes? Well, I assumed that on this one intentionally, that these forces are like this.
Okay.
Yeah, maybe wrong, but intentionally assumed it that way. So on the corresponding member that is attached to it should be the opposite of this. But you're right, once we solve it, we'll see that the assumption was not correct. So, and obviously for this free body diagram of the whole structure, we also draw its free body diagram. Here I have one force. Here I have Ex, Ey. Given that this is a two-force member, here, although it's a pin, I have only one unknown, which is this Rd, okay, in that direction, which is going like this. So that's the free body diagram for that structure, for that. So the next step, step 5, was now start with a free body diagram that has the least number of unknowns. Solve for as many unknowns as you can, move to the next. So let's see. Here we have 1, 2, 3, 4. Here we have 1, 2, 3, 4. 1, 2, 3, 4, 6. And this one, as you recall, for a two-force member, that free body diagram, in a sense, has already been used. We cannot find any unknowns from that. Because no matter what equation of equilibrium you write, you get 0 is equal to 0. We have already used equations of equilibrium, in fact, to prove that these two forces are equal in magnitude, opposite in direction. So this is always useless. So of all these, this one has the least number of unknowns. So I will start with free body diagram number 4. Write summation of forces along x equal to 0. I have negative fx, negative 80 equal to 0. So f of x comes out to be negative 80 pounds, which means the assumed direction is wrong. So I have to change that on all diagrams that disappear. This should be this way, and on this one should be that way. And we found it. So I put a check mark. As I find these unknowns, I just put a check mark next to them, and that's it. Okay? So keep track of how many unknowns I have left. Summation of forces along y is equal to 0. I get negative Fy minus negative 80 is equal to 0, or Fy also comes out to be negative 80 pounds, which means, again, the assumed direction, again, is wrong. So I would change that here and change that here. Okay? And now I've used up free body diagram number 4, so I'll just cross that out. So I have 1, 2, 3 more free body diagrams to use. And let's see which one has the least number of unknowns. Here now I have 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. All of them only have 4, right? So it doesn't matter which one I start with. I would then use this one. How about that? I'm going to start with 2. And what I will do, I will take summation of moments about B is equal to 0. Reason for that is these two would disappear, this one would disappear in the some moment equation, and I only have this known and this unknown, so I have only one unknown. So summation of moments would be what? F would be 2 over this, I guess this is from the remnants of the other wrong direction. So I have this one, which would make a negative moment, 2 over the square root 13 times RC times this distance, which is 3 feet. And then I have, I'm sorry, yeah, this one would be that. And then I have negative Fy, which is 80 times this distance, which is 4, right, is equal to 0. That's it. Those are all the forces that I have. So as you can see, RC, if I can simplify this a little bit, 2 comes out to be negative 160, okay? Square root 3 divided by 3 came out to be negative. That means the assumed direction for RC is wrong. So before doing anything else, I should change that. So I'll change this. So this is the correct direction then. So this is acting this way and this way. And I gave you the answer last time then, so once I make that correction, RC is going to be 192.3. So as I find these, I would put a check mark on them, on all those diagrams that they appear. So I have this one, and obviously, of course, here, and here, and here, right? Yes?
That's root 13, right?
Oh, sure, yes, square root of 13. But the answer is right.
Right.
Okay, sure. Any other questions? Okay, so I have still 2 more equations here that I haven't used. So I will write summation of forces along x is equal to 0. That will give me RA, okay, minus BX, right, plus 3 over square root 13 RC, which is 192.3, okay, minus 80 is equal to 0. So if I simplify that, RA minus BX is equal to 80 minus 3 times 192.3 divided by square root of 13. So that's one equation and 2 unknowns. Summation of forces along y is equal to 0 will give me negative Fy, negative 80, plus 2 over square root 13 RC, which is 192.3, minus By, and that's it, is equal to 0. So from that, I can get actually By, which comes out, and I have the answer here. By results as 26.7. So again, I check that off wherever it appears. This is found, and that's all, right? So I have now exhausted all equations of equilibrium on this one, so I don't need that. I've got everything I wanted from this diagram. So I have 2 more diagrams left. This one has 3 unknowns. This one also have 1 to refund that one. So I have also 3 unknowns. So again, I can use either one. So I'm going to use this one, okay? So I will go to number 1. I will take summation of moments about E is equal to 0. If I do that, T is of course 80 pounds. So I have moment of T would be 80 times that distance is, okay, this is 3 because this is 1. So 80 times 3 would be positive, counterclockwise. And Bx also makes a counterclockwise moment, that is times 4. And then moment of this guy also would be positive. By, I have that, I have found By, so it would be plus 26.7 times distance 3 is equal to 0. So you can immediately see that Bx comes out to be negative. And I have the answer here, so I'm just gonna give it to you. Bx would come out to be 80 pounds. Obviously, in this case, as you can see, the negative, so that means I would change it here, put a check mark on that. I can also put a check mark here. Everywhere that it has appeared. So I know, keep track of all the unknowns. So if I use now, so let me correct that then. Okay? So in that same diagram, now if I write summation of forces along x is equal to 0, I have Ex, right, minus Bx, 80, okay, plus T, 80, equal to 0. So Ex turns out to be 0. Okay? And then I have one more equation that I haven't used, summation of forces along y is equal to 0. So I have By, which I had that here, 26.7, By plus Ey is equal to 0. So Ey comes out to be negative 26.7 again, which means the assumed direction is wrong, so correct that. Okay, Ey, I found it. Okay, and Ex, okay, and done with that. So get rid of this now that I've made that correction. Okay, so the only unknown I have not found yet is what? Ra. Since I have that equation and I have Bx, right? So I can put that in there. So from this equation, I get Ra, okay, which would be Bx, okay, which I found 80, okay, plus 80 minus whatever that 3 times 192.3 divided by square root 13, and Ra, I have the answer, comes out to P, okay, Ra, okay, where is Ra here? Okay, oh, I see, it's called it AX, 160 pounds. Okay, 160 pounds. Doesn't sound right from this calculation. But anyway, that's what it comes out to be. Because that cannot be 0, right? Unless that is divided by this, I don't know. Figure that out. So that's it. But you notice now, there's one equation, yes?
For our equation, yeah, that one, because when we found Bx's direction was wrong, do we have to flip the sign in that equation?
Oh, yes, that is correct. You are, good point, 2 points. Yes, so the Bx, we assume that is wrong, so that actually would be right. So that would give us, in fact, 80 minus 80, right? So that's why. So this should be 160. Okay. All right. So you notice now that we still have, of course, we use this one, right? But there's one Freebody diagram we didn't use. So if you use this, you can check and verify if the answer that you got satisfies the equations of equilibrium, okay? Which they should, right? Because these two actually, this is the opposite direction. These two should cancel on each other, right? Okay, so at least we redid this one. Okay. Any questions? I'm going to do a good problem. This was actually one of the final exam problems a couple of years ago. So it's a good one. Must be a good one, right? If it was worth to be a final exam problem, must have been a good one. Yes.
So obviously these are a little longer and more involved than
Yes.
some of the other stuff.
Yes.
Will we still, will it just be less problems on an exam, or how
Oh, I
do
see.
an exam?
Well, good question. In fact, you will see from this problem I'm going to do that usually the type of frame problems on the exams are such that you don't have to draw too many Freebody diagrams. In other words, there are not too many members, like 4 or 5 or 6 or whatever. In fact, I did one problem in the other section, which I'm not sure I started that in this section or not. You'll find in those videos that it was too long and we just couldn't finish it in even 1 hour. So no, the answer is no. They will be practical questions. In fact, I'm going to do one right now. So if we can finish it in 25 minutes, that means in the final we have 3 hours and 5 problems. So not bad. So okay. So this was the problem.
Yeah.
And please remember, I like pulleys.
Is it Mohammad of inertia? Is that
I think there's might need to be some more centralized on it.
Different color. We have the white and we may as well use that. So you be the judge if this is an easy problem or not so easy problem. So we have this crazy looking frame. It is designed to hold this 700 pound, and the way it is, you have a pulley that this is basically attached to it. This pulley, if you pull this string, can obviously raise this weight. Of course, this is static. We're not raising it. This is statically in place. Okay? The question is, again, find forces at every single joint or every single connection of this system. Yes?
How far down does the
You don't need it.
Oh,
You just have the angle, I'm sorry. You just need only this piece of information. That's it. That's all, that's good. Okay. All right, any questions? So, let's not these pictures or drawings or things like that scare you, okay? Go step by step. Step number 1. X, Y coordinates. So this is the X, Y coordinates. Step 2, take everything apart. Now, okay, I'm gonna start with this little guy here, E. The pulley, this is a force of 700 pounds. I call this T and T. So let's call this Freebody diagram number 1. Then you have this pulley, okay? You have this force, which is T, because this is what comes to this, and this force T, and it is connected to this pin at C. So you have this and this. I call CX, CY. So why don't I call this 2? Clear so far? No problem. The Freebody diagram. Okay. So now let's look at this other pulley. Okay. Number 3. Okay, you have this force coming here, T, at 16 degrees. It is connected to this beam at B, so let's say you have this force Bx and By. So I call that Freebody diagram 3. Okay. Now we have this guy here. A, okay, B, and C, right? At C, you have to be very careful. What do you see at C? Obviously, I have this C, oh, let me do it in a different color. I have this CX and CY, right? But in addition to that, you see, I have another force, T, here. Can you see that? Because this cable on one side, right, goes around, and the other side is also carries a force, T, attached to pin here, right? Then pulleys attached to the pin there, which of course through these 2 connections. So you have 3 forces there. So that's really the key part, okay? Then what happens at B? At B you have this member, right? Which is what? 2-force member. So you have this force, I would call that, and would be at 45 degrees, because that's 4 and 4. So this is 45 degrees. So let me call this force of dB, right? And then, of course, in addition to that, pulley was supported by this member at B, which, of course, is through these 2 forces. So you have Bx and By here. And at A, you have, of course, this usual AX and AY. Is that easy?
What
No.
happens if you consider the pin that the tension's pulling on as part of diagram 2 instead of diagram 4?
Which one?
diagram
so-
2, so you have a tension pulling downwards on diagram
You
2,
mean you
and
still-
then and then the pin is pushing against the thing, so in 4, the tension would then be a force
See,
upward.
this is, I mean, you need to, of course, we had given the, top the top view also. You look at it like this, I mean, this is what you have. At C, this is what you have. If you look at top view, right? This is what you have. You have a pin, right? This is a pin. This pin is holding this pulley, right? That's pulley. This is C from top view, looking at like this, right? So if you're looking at it that way, there's a pulley that this pin is supporting, right? So there's a force that this pin exerts on that pulley and vice versa. That's the force, what I have given here. But then this cable is attached here. So it's going like this, right? So you have, that's where those three forces are coming.
So I'm saying, what if instead of considering the actual pin part as part of 4, if you consider the
That-
pin
same
itself
thing.
as part 2?
Same thing, doesn't matter. Any other questions? Okay, so that's why I say that free body diagram are really the key. So in fact, I did not write down, this was step 3, right? Which is free body diagrams. And step 4, recognizing two force members. So the first 4 steps are the key. Once you establish that, you start again with the free body diagram with the least number of unknowns. That would be 1. There's only 1 unknown there, so I'm going to use 1. And all I have is just summation of forces along y is equal to 0. So you have 2t is equal to 700, or t is equal to 350 pounds. So this is given, this free body diagram is gone. Here, this is 350, this is 350, in other words, you found these. And that's the next logical free body diagram, because it has only 2. All the rest, more than 2, right? So I'm going to use free body diagram number 2. Do that, you just write summation of forces along x equal to 0. That'll give you Cx minus 350 is equal to 0, so Cx is 350 pounds. Summation of forces along y is equal to 0. You have Cy minus 350 equal to 0, so Cy is 350 pounds. And both directions apparently where the correct assumption was made when I chose these directions. So this is done, this is done, this free body diagram is gone, right? Then, right here, 2 unknowns. So I will go with free body diagram number 3. I have Bx, okay, By, and this is, T is 350, this T is 350 at 60 degrees, right? So, summation of forces along x is equal to 0, right? You have negative Bx, okay, plus 350 minus 350 cosine of 60, right? Cosine of 60 is equal to 0. Cosine of 60 is 1/2. So you have 350 minus 175, which is 175. Bx would be 175 pounds. Okay. Which I believe I have that right here. Okay. And then you have summation of forces along y is equal to 0. So you have By minus 350 50 cosine of 30 is equal to 0. Okay, so that would be give you by would be 350 square root 3 over 2. Could you give me that number? 175 square root 3. How much would that be? Although I have that here, but it's like I've left it as the square root of
303.
303. Oh, okay. So V1 is 303. Okay, so this three-body diagram is gone. So now let's go here. I found Bx. I found By, right? What else? I have Cx. Cy, right? And I have only, and of course T is given. So I just have 1, 2, 3. So I'm using that free body diagram. I can find all the unknowns. So let's redraw that and put all the forces that we have to make things a little bit more clear. I have Cx, which is 350. Okay. Cy, which is 350 plus T, which is also 350. So I have 700 pounds here, right? Bx here is 175 pounds, and then By, which is 303. Then I have this one, which is unknown, f of d, b, and then ax and a y. So this is free body diagram number 4. Okay, that's all I have. Okay. Okay. So from that, easily I can take summation of moments. Of course, first thing is first. Resolve these into components. This would be FDB, the square root 2 over 2, FDB, square root 2 over 2, cosine of 45 degrees. Okay? So if you do that, you just take summation of moments about A is equal to 0, right? So you have 7, this one and this one and this one, these two all go through that. So you only end up with one unknown. So you have 700, negative 700, okay, times this distance, which is 8. Okay, moment of this, plus moment of 303 times 4, okay, plus moment of FDB, the square root 2 over 2, also times 4. I'm sorry, both, all, that one's also negative. All these generate a negative moment, okay? So you get FDB comes out to be a negative number, and I have the answer here. FDB, okay, TDB comes out to be, okay, I have 2,409 pounds. 2,409 pounds came out to be negative. That means the assumed direction is wrong. So I just have to change these directions, and this one, that means this is like this, right? And that's it. So that would be the force. Okay. Again, as you can see, of course, I can now solve for summation of forces along X. equal to 0. So I have AX minus 2,409 square root 2 over 2, okay, minus 350 plus 175 is equal to 0. AX comes out to be, I have the AX, 1,880. Summation of forces along Y is equal to 0, will give me AY plus 2,409 square root 2 over 2, okay, minus 700 and minus 303 is equal to 0. AY comes out to be 700 pounds. Positive. So all the unknowns were found. Okay, we have used up this free body diagram, and as usual, we end up with one free body diagram that we haven't used. If you want, you can use that to verify your answers, right? So that means this is one force at F of dB, right? We have AX, AY, and then we have cut this one, so that's T. So if you write summation of forces along X, Y, summation of moments, they all should go to 0 on this diagram, which you use it to confirm your answers, verify.
So, I noticed you didn't do a free body diagram for the 2-force member. Do we need to do that, or is that?
You mean, I did here. Oh, you mean here? No, I didn't, because it's, as I said, free body diagram for a 2-force member doesn't give you anything.
Okay,
Yeah.
so we shouldn't necessarily include that.
You don't have to, but be careful though, what is more important, that 2-force members represent just one unknown force as you do the other diagrams. Yes, there was another question? No? So we made history, we did 2 problems, unbelievable. Okay. Okay, so we'll do more problems on Friday. Okay, any questions? Great, thank you very much.